Today we are going to see chapter 1, number system. What are the types of number system? Number system include decimal, binary, octal and hexadecimal. Each system have its number base. Binary has a base of 2, octal has a base of 8, decimal has a base of 10 and hexadecimal has a base of 16. Decimal number system. It uses the base of 10. The largest value of a digit is 9. Each place represents a different multiple of 10. These multiples are also called as weighted values. Now, if you see in this diagram, these are the portions or right of the decimal point and these are the portion of the left side of the decimal point. So after the decimal point, the first digit is equivalent of 0.1 and the second digit has a weightage of 0.01 and the third position is 0.001 like that. Similarly, the left of the decimal point is the first one is 10 raised to 0, so the equivalent weightage is 1 and the next position is 10 raised to 1, so equivalent is 10 and the next one is 10 raised to 2, that is equivalent of 100 and so on. Next we see binary number system. Most modern computer system operates using the binary logic. A computer cannot operate on the decimal number system. A binary number system uses only two digits, namely 0 and 1. It uses the base 2. The binary digits are also called as bits. The weighted values for different positions for a binary system are, see here, this red numbers are the decimal, that is the right position of the decimal point, and these are the left side of the decimal point. So after decimal point, the right position, the first place is equivalent weightage of 0.5 and the second position is 0.25 and so on. Similarly, the right position weightages are 1, 2, 4, that is power of 2, 8, 16, 32, 64 and so on. Then next we see octal number system. In this octal number system, the base is 8. Each digit in the octal system will assume 8 different values, that is from 0 to 7. The placeholders are the rightmost bit has a place value of 8 raised to 0, that is equivalent of 1. And the next position is 8 raised to 1, that is equivalent of 8. And the next position is 8 raised to 2, that is equivalent of 64. Then next we see hexadecimal number system. The base of hexadecimal number system is 16. The number of values assumed by each digit is 16. The values include digits 0 to 9 and letters A, B, C, D, E, F. That is, the equivalent of A is 10 and the equivalent of B is 11, and for C that is 12, 13, for E 14 and the equivalent of F is 15. 0 represents the least significant digit, whereas F represents the most significant digit. Now we see the place value of hexadecimal placeholders. The rightmost bit weightage is 16 raised to 0, that is equivalent of 1. And the next one is 16 raised to 1, that is 16. And the next one is 16 raised to 2, that is 256. And the next one is 16 raised to 3, that is 4096. Now we see some of the conversion. That is, first we see decimal to binary conversion. The given by decimal number is 156. When we divide the 156 number continuously by the base, that is 2, then we get reminders. Those reminders we have to consider from bottom to top, that is the equivalent of binary. Now next we see decimal to octal conversion. In this, the given decimal number is to be divided continuously by the base of octal number, that is 8, and whatever the remainder we are getting from the last remainder is most significant bit, and the first reminder, that is least significant digit. So the equivalent of octal is 5644. Then next we see decimal to hexadecimal conversion. So the given number is to be divided by 16, and whatever the remainder we are getting from bottom to top, that we have to consider as most significant digit to least significant digit. Now next we see binary to decimal conversion. In this, the given binary while converting into decimal, the equivalent weightage is to be multiplied with that corresponding bit, so that, see here in this case, the weightage is 2 raised to 0, that is 1, and the next one is 2, 4, 8, 16. So the bit is to be multiplied with those weightages, and finally these value is to be added to give the final value of the decimal equivalent. And next we see binary to octal conversion. The given binary number is to be divided in a group of 3, and the equivalent octal value is to be right, so that we get the octal equivalent value is 65043. Next we see binary to hexadecimal conversion. The given binary number is to be divided in a group of 4, and the binary of the 4 bits is to be given the equivalent of hexadecimal, like 000 means the equivalent is 0, 1101 binary equivalent is D. Similarly, 1101 is D, 0100 is 4. Thank you.